So welcome to topic 8, which we will introduce organic chemistry with acids and bases. So there's quite a lot of material in the SL portion, so we're going to break it up into a series of 5 different units. And today's lesson, we're going to be looking at the theories of acids and bases. So let's just kick on. So by the end of this unit, you should have a concept of the Bronsted idea of a acid and a base, a discussion around what an amphoteric species is in terms of Bronsted-Lowry, and conjugate acid-base pairs, which are also a cornerstone of Bronsted-Lowry acid-base theory. And by the end of the unit, you should also be able to deduce the Bronsted-Lowry acid and base pairs in a chemical reaction, and also deduce the conjugate acid or conjugate base through Bronsted-Lowry in a chemical reaction. Right, so let's look at some nature of science to start off with, the idea of the acid-base hypothesis. So we're going to basically looking at the development of acid-base theory. So the early Greeks, they classified substances based on their taste. Okay, so sweet things, salty things, and sour things, for example. And they defined alkalis, or basically water-soluble bases, were known to neutralize things with sour tastes. So therefore, their definition of acids was around the fact that it had a sour taste, like, for example, vinegar, ethanoic acid. Then we move on to 1777, where French chemist Antoine Lavoisier burnt the element phosphorus and the element sulfur with elemental oxygen. These compounds were acidic when dissolved in water. Therefore, his argument was that acids contain the element oxygen. This actually created the word oxygen because a lot of Lavoisier's works was around the element oxygen, because ox means sour and gens born of the Greeks. Okay, so it's oxygen is basically if an element, a compound contains the element oxygen, it's going to taste sour, and that idea of sourness comes from there, the Greek definition of the acid. And in 1809, Humphrey Davy, the British chemist, questioned this because he noticed that, well, hey, wait a minute, hydrochloric gas, hydrogen sulfide, hydrogen tellurium were also acidic, but hey, wait a minute, there's no oxygen. So he challenged the concept that acids always had to contain oxygen, so the theory moved on. So moving on through history, now more into the later 19th, early 20th century, we looked at Arrhenius, and basically what Arrhenius proposed is that salts form ions in solution, even without an electric current. Hence, acids were positive, so he proposed, well, they contain H+ or protons, and bases released OH- or hydroxide ions. But however, this did not explain outside of aqueous solutions, or for bases that do not contain this hydroxy group. Remember, of course, from TOK that the best hypothesis or theory is the one which is able to predict best. So Arrhenius had problems because he couldn't predict that, well, this is a base, but it hasn't got no hydroxide group. So then we move on to Bronsted-Lowry, which is the basis of most of the SL material for IB. And they argued that acids are proton donors and bases are proton acceptors. Therefore, ammonia can be introduced as a base because it accepts protons. Then we have Lewis using his dot structures defining acids. Okay, so Lewis dot cross diagrams, remember those from earlier in the course. Okay, defining acids as electron pair acceptors and a base as an electron pair donor. For example, that means that both ammonia and boron trifluoride can now be explained as bases. And of course, that's also what we're looking at when we're looking at some of the complex chemistry that we looked at earlier in the year when we looked at Lewis dot cross diagrams. Okay, let's do a quick learning check on who proposed which or what in terms of hypotheses. Okay, so who proposed that phosphorus and sulfur oxides make acids? Okay, mentioned oxygen, so that must be the great French chemist Lavoisier, who lost his head, of course, in the Revolution. Hydrogen chloride does not contain oxygen. Okay, so who made that counterclaim to Lavoisier? which challenged his ideas of acids. Okay, that of course was the British chemist Davy. Acids give off protons or hydrogen plus ions. That was of course Arrhenius, and then that was extended further with acids and proton donors and bases as proton acceptors by the two chemists Bronsted and Lowry, and of course the only one left. Acids are electron pair acceptors and bases are electron pair donors, of course, is Lewis. Okay, so hopefully you got those all correct. So now we're going to look at the Arrhenius acid and bases hypothesis in a little bit more detail. Okay, so an Arrhenius acid produces proton ions or hydronium ions in an aqueous solution. So for example, hydrochloric acid. Okay, so it's going to produce H plus ions and chloride ions. An Arrhenius base, on the other hand, produces hydroxide ions. For example, sodium hydroxide will produce sodium ions and hydroxide ions. However, there is a problem because some bases don't actually have hydroxide ions, which is a problem for the Arrhenius acids and bases hypothesis. So, with that in mind, a Bronsted-Lowry acid is a proton donor. So, for example, water. Water donates protons to water, so it becomes the hydronium ion, the acid. And a Bronsted-Lowry base is a proton acceptor. For example, ammonia, which accepts a proton to become the ammonium ion. Now, a proton is really just a hydrogen atom that has lost its electron, which is exactly what it is. It's basically just the nucleus of a hydrogen atom. So a Bronsted-Lowry acid is a proton donor. A Bronsted-Lowry base is a proton acceptor. Okay, so the base accepts a proton from the acid to become the conjugate acid. Other way of looking at it is that the acid gives a proton to a base to become the conjugate base. Okay, so for this particular example, ammonia is the base because it accepts a proton from water, the acid, to become the conjugate acid ammonium, and a water gives a proton to ammonia to become its conjugate base hydroxide. And there we go. These are known as acid conjugate base pairs. So by the Bronsted definition, this means that ammonia is a base in water because it takes the proton from water, and water itself actually acts as an acid because it's giving its proton to the ammonia. So in terms of the conjugate acid-base pairs, in this equation here, for example, basically hydrogen carbonate acts as an acid, okay, because it gives a proton to the water, which therefore acts as a base. So that means the conjugate acid of the water, which is acting as the base, is going to be hydronium, and the conjugate base of the acid is going to be the product of the loss of the proton, which will be the carbonate anion. So an important term also, which you have to be familiar with, is amphoteric. Okay, an amphoteric species, usually a salt, can act either as an acid or a base. So for example, aluminium oxide or alumina is a base because aluminium oxide reacts with acid to form aluminium chloride and water, but it can act as an acid because aluminium oxide reacts with a base, strong base like sodium hydroxide, a strong alkali, to form sodium aluminium tetrahydroxide. Okay, that's amphoteric, not to be confused with amphiprotic. Okay, amphiprotic is a type of amphoteric substance that specifically can act either as an acid or a base by accepting or donating hydrogen ions. Okay, so water is a case in point there. So when water is in the presence of an acid, it acts as a base by accepting the proton from the strong acid. And when it is in the presence of a base like ammonia, it then acts as an acid by providing a proton to the ammonia. Okay. Right, so for a final learning check, let's just label the acid, base, conjugate acid, and conjugate base in each of the reactions below. So pause the video now, look at the equations and label them appropriately, then play the video to see if you are correct. Okay, so the first one, the hydrochloric acid, it's an acid, so there we go. Then we have the reacting with the base hydroxide to give the conjugate base there, chloride ion, and in this case water will act as an acid, so it's going to be the conjugate acid. In the second example, water will act as a proton acceptor, so it will be the base, then the acid will of course be the acid. The hydrogen sulfite is going to be a proton acceptor, so it will be the conjugate base, therefore the hydronium ion will be the conjugate acid. So hopefully you have a grasp of those four terms and also an understanding now of the principles of the Bronsted hypothesis of acids and bases.